Hi everyone, my name is Max Leamy and today I'll be presenting the motion of a falling object lab. As an introduction, in this lab we recorded an object fall with constant acceleration due to gravity in a constant direction. Then we tracked the displacement of the object and compared the results with a computer model representing constant acceleration and no drag, and a computer model representing constant acceleration with drag. From the experiment, it was determined that the observed data was very similar to the model without drag and almost identical to the model with drag, with a proportionality constant of 0.002. Here's my video. For the physics concepts, the updated position formula, Newton's second law, or updated velocity formula, basic kinematic equation for constant acceleration, and the kinematic equations for the x and y directions during projectile motion were used in the experiment. The updated position formula relates change in position to average velocity multiplied by the change in time. Newton's second law demonstrates that the change in velocity is related to the net force on the object, the mass of the object, and the change in time. The kinematic equation for constant acceleration relates change in position to the velocity of the object times change in time, and the average acceleration of the object times change in time squared. The kinematic equation is simplified for the x direction because there is no acceleration horizontally as an object falls. The acceleration in the y direction is the gravitational force on the object. Three models were used for this experiment. This model is the experimental model. For this model, I created a coordinate system and tracker to represent displacement of the sneaker ball and measured the y-coordinate of the ball at each frame of my video. This model is the computer-generated model without drag, which generates the position of the object over time if the net force is only due to the acceleration of the ball due to gravitational force. The velocity versus time graph has a constant slope because the acceleration is constant. This final model is the computer-generated model with drag, which generates the position of the object over time if the net force is due to the acceleration of the ball due to gravitational force, and the drag force that is related to the gravitational force and the square of the speed or magnitude velocity graph. The equation for the drag is represented by negative b times the magnitude of velocity squared, where b is the proportionality constant that I determined best fit my data. The velocity versus time graph has a varying slope because the acceleration is not constant in this model. For my experiment, I recorded a sneaker ball falling from my height to the ground. To track the ball's displacement, I created a coordinate system and tracker that positions the y-axis along the center of mass of the sneaker ball and positions the origin at the point where the ball makes contact with the ground. I then created a reference distance of the sneaker ball's radius and a reference distance of the total height the ball fell to ensure my displacement results are accurate. I then measured the position of the ball during each frame of the 0.55 second video I chose and plotted the results. The initial conditions of the experiment are the initial velocity of the ball is the vector 0, 0, 0, and the initial position of the ball is the vector 0, 1.678 meters, 0. The ball has an acceleration of negative 9.8 meters per second squared as soon as the ball is released from rest. The system of the experiment is the ball and the surroundings of the experiment are the rest of the environment. To code the computer model for the experiment, I first added the mass of the sneaker ball into the code and set the delta t equal to the time between one frame of my footage. I then set the maximum time t to 0.55 seconds. Then I added the initial position vector and initial velocity vector to the code and set the fnet vector for the computer model without drag equal to the vector 0, negative mg, 0, and the computer model with drag equal to the vector 0, negative mg plus drag with my chosen b value, which was discussed how to calculate earlier, 0. Finally, I added arrows to the model to show the net force on the ball due to gravity and to drag. For the discussion, I plotted the exposition results of both the computer models compared to the experiment over time. The computer model data without drag has a constant acceleration throughout the entire time measured. The computer model data with drag has a non-constant acceleration throughout the time. The experimental data slightly overestimates the position of the ball when compared to the computer model without drag at the end of the time. This overestimation is fixed with the computer model with drag. Using a proportionality constant of b equals 0.002, the computer data with drag almost perfectly matches the observed data. This implies the experimental data experienced some drag force. Some error during the experiment may have caused the results, including human mistake when dropping the ball and applying a force, and recording on a slant, as well as error when using tracker because the ball was moving so quickly. In conclusion, from this experiment, we learned that we can track the motion of an object with constant acceleration very accurately, especially using our drag model. Our model can be used to predict the position and velocity vectors for an object falling at constant acceleration well for a short delta t and with a small drag force. For the what does it mean and what if questions, none of our models predicted a terminal velocity over the short time period used to track the ball. If the ball accelerated for a larger time, the drag force would become large enough to cancel out the acceleration due to gravity, and the object would reach a terminal velocity. If the object were thrown downwards, the terminal velocity of the object would not change. It would just reach its terminal velocity faster because it would have a larger initial velocity, but the same acceleration to get there. Thank you for watching my video.